In this problem from gravitation that has been asked, we have an hypothetical spherical galaxy in which the mass density is given by this. What does this mean? This means that the galaxy is everywhere. The mass of the galaxy is everywhere, but the density keeps on decreasing as one goes away from the center of the galaxy. Now, there is a planet which is rotating at a radius of capital R. Let's find out what is the gravitational field due to this spherical galaxy at that radius of capital R, okay? So for doing that, we need to take a spherical shell of the galaxy, okay, a thin spherical shell. And let's first find out what is the gravitational field due to this small shell, okay? We need to find out that first. Now, I have taken the shell in a manner which is at a distance of x, and the shell has a thickness of dx. Of course, we are finding out the gravitational field due to this shell at a distance of capital R. Please understand that the radius of the shell x is less than r. We are considering only the shells which are less than the radius of capital R. Okay. Why are we considering the shells which we have where the radius is less than capital R? That's a question I am keeping open. You have to think about it and put that in the comment section if you understand that. If you don't, then also put a comment. I would reply to that. Now, what is the gravitational field at that radius of capital R for this mass? First of all, we need to know this small shell. What is the mass of that? The mass of this small shell would be equal to its density at that point multiplied by its volume. Now, what is the density of the mass at this radius of x? The density would be equal to k by x. And what is the volume of the shell? The volume of the shell would be equal to its surface area, which is 4 pi x square multiplied by its thickness dx. So this is the mass. If this is the mass at a radius of capital R, what would be the field? See, for a spherical shell, the field at a distance r is equal to the field by a concentrated mass which is at the center. So I can write that the gravitational field by this shell is equal to capital G dm by r square. Now put the dm over here. I get g k 4 pi x square dx by x r square. One of the x I can cancel out. So this is the gravitational field by this shell. So what is the total gravitational field at that radius of capital R? It would be integration from 0 to capital R gk 4 pi by r square into x dx. If you do this, you get gk 4 pi by r square into r square by 2. The radius term goes away and I am left with 2gk pi. So this is the gravitational field at that radius. Once you have got the gravitational field, you just need to find out what is the gravitational force the planet is what is the gravitational force the planet is experiencing. For that, you need to know the mass of the gravitational field. Let's call that as capital M, and I get the gravitational force as equal to 2 gm pi. Now, the planet is rotating in a circular path, so the centrifugal force must be equal to this gravitational force. What would that be? So I can write capital M omega square capital R. R is the radius, is equal to twice g capital M k into pi. The M cancels out and I get omega square is equal to twice g k pi divided by r, or omega is equal to under root of this term. Once we have got the omega term, finding out the time period is very easy. We are finding out one time period of revolution, right? So that would be equal to 2 pi by omega. So 2 pi divided by root over of twice g k pi. We have a root over r on top as well. So finally, what is the time period that you get? This is nothing but is equal to root over of 2 pi capital R divided by gk. Okay, a fairly easy problem to solve. But once again, think, why have I taken x varying from 0 to capital R? There must be mass which is beyond the planet as well, right? There will be masses. Why have I not considered the mass which is beyond the planet? Let me explain once again. This is the center of the galaxy. The planet is over here. And I have considered the mass which is in this region, that is between 0 and R. And I have not taken the mass which is beyond the radius. Why is this so? Think about it. Thank you.